Hello, thank you for attending our webinar. Our agenda will describe pre-purification of peptides with flash chromatography. We will find that, especially for smaller peptides, flash may be all that you need. Method development techniques for peptides for both flash and preparative HPLC, which will cover both gradient methods and the importance of pH control. And we will end with an overview of column selection. We will discuss the effects of pore size and reverse phase alkyl chain length. During the webinar, we will also show how the choice of reverse phase column is affected by the use of highly aqueous mobile phases. Many people purchase peptides from a company that specializes in producing them. So why do your own purification? Well, you can save time because you can get your peptides faster. You can purify a small amount immediately to get started on your work. You can save 30% in the cost. And also, if you have peptide that's been sitting around, you can polish it up again. Costs are from a local peptide synthesis and purification company. Flash chromatography is a lower resolution purification technique that uses less expensive columns and equipment. You have a choice of column selectivities, such as different types of C18 or C8, allowing pre-purification prior to preparative HPLC. Impurities eluting with the peptide with one column might be resolved with a different column, and we will see an example at the end of the presentation. Prep HPLC sample load is limited by the sample loop size and the solubility of sample in the injection solvent. By removing impurities that differ greatly from the desired compound, the material that is left has a similar polarity as the compound that you want. This makes it easier to dissolve the sample in a good solvent for high-pressure chromatography. Method development is very easy because ReadySep flash, prep, and analytical columns have the same chemistry. For the flash chromatography experiments, the NextGen 300 and ReadySep RF Gold reverse phase columns were used for all experiments. Analytical scouting HPLC used ReadySep analytical columns, either 4.6 by 150 millimeter or 2 by 50 millimeter. This is a prep HPLC run, and the compound was dissolved in DMSO because of this late eluting nonpolar material. It isn't soluble in water. The problem with DMSO is that it is a stronger solvent than this mobile phase. In the previous slide, I mentioned sample solubility as a limiting factor, and this is just such a situation caused by nonpolar compounds. The DMSO causes the peaks to run together as the sample loading is increased. This limits my loading to only 13 milligrams before the peaks touch. The tan section defines a collection time window, so I only collect the fractions that interest me. This is the same peptide as our earlier run. The red circle denotes nonpolar impurities, which are water insoluble. A gradient similar to the prep HPLC run was used. The red box denotes the collected fractions, and there was 40 milligrams of material recovered from those fractions. After flash, we can load 3 times the mass in a single run compared to the original purification. The ability to dissolve the purified sample in water allows improved resolution compared to the DMSO injection and also allowed higher loading. Mass spectrometer verifies the correct peak was collected. The removal of the nonpolar material provides the potential of much greater throughput. We could end this run at 8 minutes after the compound has eluted and start another run, so we can get 2 runs in the same amount of time. If we combined the improved higher loading and shorter run time, we get 6 times the throughput in the same amount of time. The Torrent AQ is optimized for reverse phase and very large samples. It is great for initial purification of gram scale samples, and the optional sample load pump is used for large dilute sample and also for solvent switching. Flash chromatography can be an efficient method for purifying peptides by itself. This cyclic peptide, phallocidin, was purified on a ReadySep RF Gold C18AQ column. This compound binds to actin in cells. The method was developed on a ReadySep Prep C18AQ analytical column on an Analytical HPLC as described in the next section on method development. The C18AQ is resistant to phase collapse and gives better resolution in highly aqueous mobile phases. Method development was very simple because the analytical and prep columns have matching chemistry and selectivity. All-Wavelength Collection was used during this run too, as depicted by the yellow trace. Here we have a more complex sample. This is phalloidin, another actin binder. These peptides are conjugated to various fluorescent molecules to visualize and localize actin filaments in cells, as seen in the colorful picture. We can see an impurity close to the desired compound. However, the analytical HPLC is clean. There is no preparative HPLC cleanup required. One quick word about all-wavelength collection. A customer used the AccuPrep HP150 for purification. They noted impurities eluting between 32 and 33 minutes and were able to cut those fractions, resulting in a product with improved purity. Those impurities were not visible by the single wavelength UV trace, but showed up very clearly with all wavelength collection. We will now discuss how we calculated the gradients for the flash runs. The same method is used for flash and preparative HPLC. This uses the time on target algorithm in the cited paper. Please note that if you use an AccuPrep, all of the calibrations are built into the system using the AccuPrep defined scouting gradients. There will soon be the ability to use your own analytical scouting runs to calculate focused gradients. On your prep system, do an isocratic run with a model compound and set the retention time as desired. Universal test mix used with Teledyne ISCO systems is good for reverse phase and some other column chemistries. Note the solvent composition used to set the retention time. You don't want the retention to be too early, or there will be no resolution from early eluting compounds. For most purposes, 6 minutes using a 150 millimeter long column works fine. For a longer column, such as 250 millimeters, I like to set a 10-minute retention, which scales from the 6 minutes on a 150 millimeter column. On your analytical system, do a run with the same compound. Use the same compound chemistry as the preparative system. Even using the same brand of columns, don't mix different types of C18. For example, ReadySep C18AQ may not run quite the same as regular C18. You will also use the same solvent system, including any modifiers. Note the red gradient. There is no isocratic hold at the start. Isocratic holds at the start confuse the calculations. Whatever time the model compound elutes is considered to be the same solvent composition as that used for the isocratic run. The difference in time between that same solvent composition and the time the peak elutes is the apparent gradient delay. The program gradient appears offset by that delay. This example shows a peptide run with the same scouting gradient as the previous slide. The peptide is thymosin run on a ReadySep C18U HPLC column. Running a peptide on the same scouting gradient, I can apply the previously measured apparent gradient delay. The solvent composition that will elute this peptide is not 50% B as depicted in the programmed gradient. After applying the apparent gradient delay, we can see the compound would be expected to elute with a solvent composition of about 20% acetyl nitrile, as seen in this calculated gradient. Or you can use the focus gradient generator built into the AccuPrep, as we will in the next set of slides, where we discuss the effects of buffers as solvent modifiers and a comparison with trifluoroacetic acid as a buffer. The focus gradient generator is based on the time on target algorithm cited earlier. The calibrations are programmed into peak track. Doing the scouting run with the AccuPrep works with your columns, no matter who made them or the media, without calibration. Why did I choose 50 millimolar ammonium formate as a solvent system? What advantages does the mass spectrometer detection give us? These runs use synthesized epidermal growth factor receptor variant 3. The first run uses the common water acetylnitrile modified with 0.1 TFA, that is trifluoroacetic acid. The calculated gradient in the center shows a late elution. The peak shape is a little odd too, although that might be due to the step gradient as well. A slight adjustment to the focus gradient causes a nice elution. Odd peak shapes of ionizable compounds suggest pH issues. The mass spectrometer trace suggests the same compound is in multiple peaks. This suggests that the compound has multiple stable ionized states under these conditions, each with its own polarity and its own retention time. This is because TFA is not a buffer in preparative HPLC. TFA is about 6 millimolar concentration at 0.1%. For this run, only 50 milligram peptide was injected with a mass of 1,600 grams per mole, which is about 0.03 millimolars, which doesn't seem like much. However, this compound is ideally eluting in the volume of about 20 mils or 1 fraction tube. So the concentration is actually close to 2 millimolar within the peak and is 1/3 the concentration of the modifier, enough to deplete the slight buffering capacity of TFA. Injecting a larger mass of peptide will make the situation even worse. Analytical HPLC injections contain so little material that TFA can control the ionization and the pH is not affected. Without the mass spectrometer, one might think that the other peaks were impurities. These peaks might not be collected, so that material would be lost and your yield would be lowered. Let's try a buffer, but now I need to make some changes to my solvent system. Ammonium acetate is soluble in the presence of methanol, but not acetylnitrile. The focus gradient generator worked first time in this run. However, we still see multiple peaks in the UV and the mass spectrometer. We will try a lower pH since this peptide has a pI of 4.5. This is the pH where the positive and negative charges for the peptide balance out, so it has a net charge of 0. I'd like to be more than 1 pH unit from the pI because small changes in pH can cause the peptide to have something other than net 0 charge, causing shifts in retention time. To lower the pH, I use ammonium formate, which buffers at pH 3.5. The peptide elutes as a single peak now and is mostly resolved from impurities. This purification would give both good purity and good recovery. I used ammonium acetate and ammonium formate because they are volatile and can be used with the mass spectrometer. Since this is a preparative LC system, only a tiny portion of the flow, microliters at any one time, gets diverted to the mass spectrometer. So I can use 50 millimolar buffer. The buffer gets diluted by the carrier solvent that delivers the sample to the mass spectrometer. These buffers, being volatile, can also be removed during lyophilization, making cleanup post-purification much easier than mineral salts. In preparative LC, removing salts or other modifiers always needs to be considered. To summarize this section, recovery is improved because of improved peak shape. The entire peptide is in a single peak, not in several peaks. We see this issue with preparative chromatography because the sample concentration is so high compared with analytical techniques. In analytical chromatography, the modifier concentration is usually very high compared to the sample concentration. Now we will discuss the effects of stationary phase pore size on peptide elution. We will see differences between peptides and small molecules, and we will provide guidance on when to use stationary phases with different pore sizes. We used methyl, ethyl, propyl, and butylparaben for these experiments. The cartoon shows how pore size distribution affects surface area. More surface area allows greater interaction with the stationary phase when the compound adsorbs, increasing retention time. As pore size increases, surface area decreases, causing reduced retention. All of the compounds show decreased dilution as the pore size increases, reducing the surface area. But what about peptides? These peptides are used for the rest of the presentation. They range from about 1600 Daltons, a small peptide or similar to a small molecule, to AS48, which is almost 8,000 Daltons. EGFR acts like a small molecule in the previous slide. It exhibits reduced retention time with increasing pore size. The retention decreases from 4.2 minutes to 4.1 minutes. However, the change in retention time isn't as noticeable as the parabens shown earlier. Thymosin has the opposite behavior. Its retention actually increases as the pore size decreases, changing from 4.3 to 4.6 minutes. AS48 continues this trend. Its retention starts at 8.8 minutes and increases to 9.1 minutes. So, what is going on here? I'll introduce the concept of effective pore size. To large peptides, the stationary phase inside small pores is inaccessible. To the peptides, that portion of the stationary phase doesn't exist. This makes the effective surface area for larger peptides smaller than that for small peptides like EGFR in the earlier slides, which can enter the smaller pores. To a limit, larger pores retain larger peptides better. My experience is the changeover from small molecule to large is on the order of about 2,000 Daltons in this context. However, note that you will hear different numbers from different people based on their test. We all agree, however, about the concept of effective surface area. So, what about alkyl phase chain length? How does that affect retention? Here's our mixture of parabens again, methyl, ethyl, propyl, and butyl again. Going from top to bottom, we have shorter chain lengths. The pore size is constant between the columns. Mixing the effects of pore size and chain length makes things more complex, as we will show later. Again, retention is decreased as we go down the series. So what happens with peptides? All of the peptides show increased retention with decreased chain length. The greatest improvement is seen when going to C8. The effect is greatest with the larger peptides. So the greatest effect is with AS48, so what could be going on? The pore size for silica-based columns is measured prior to modification. This is denoted by the red circle. C18 has the smallest pores after the alkyl phase is bonded. The pore is partially closed as depicted by the small circle. The C8 opening is larger than the C18 pore. Even with similar silica pore sizes, this makes C8 bonded phase columns more accessible to large molecules. The other thing that is happening is a change in retention compared to small molecules. Peptides tend to lie across the ends of the alkyl chain. Small alkyl chains also allow some interaction with the underlying silica. Although the reverse phase columns used here are end-capped, no C18 end-capping is 100% effective at covering all of the silanol groups, and this is true for all manufacturers. With C18, small molecules can interact between the alkyl chain due to their smaller size. Smaller peptides can act in this fashion as well. These runs are the same peptide that we ran earlier to demonstrate the need for pH control. We can compare the different types of reverse phase with respect to resolution and retention. The mobile phase is the same as that run earlier. Ammonium formate buffered to pH 3.5 with methanol as the eluting solvent. The runs on the right also used an evaporative light scattering detector. The sensitivity of this detector appeared similar to UV detection for peptides. The C18 run looks pretty good, but there is a slight overlap with an impurity. The mobile phase is mostly aqueous, about 25 to 35% methanol run in the gradient. With a mostly aqueous mobile phase, we could try a C18AQ column. This is the same C18AQ column material used for the flash chromatography examples, but a smaller particle size and packed into a preparative HPLC column. The gradient and EGFR elution time were found to be the same as the standard C18. However, the desired peptide is completely clear of the impurities. You may have heard me use the term selectivity, and this is an example of what I mean when I say columns have different selectivities. Selectivity is the relative elution of two peaks. There is a more formal definition, but this is easier to see. The desired peptide elutes at the same time on the C18 and the AQ column using the same gradient. The impurities elute earlier on the AQ than the C18, showing a change in selectivity. Now let's look at the C8 column. Again, there is improved resolution from the impurities compared to the standard C18. However, the C8 column elutes this compound with less methanol than the C18 columns. The focus gradient generated caused the elution time to be similar. Because the focus gradient has the same 10% range, I only highlighted the end of the gradient. The C8 column needed 6% less methanol to get the same retention. If a compound needs less methanol to elute on the C8 column, it essentially elutes earlier than the other columns using their gradient methods. Earlier, I showed how the EGFR eluted later as I shortened the reverse phase alkyl chain length, but the effect was small. I also showed that this peptide eluted earlier as the pore size became larger in common with small molecules. Here we have two variables being changed at once, the pore size and the chain length. The C18 and C18AQ have 100 angstrom pores, while the C8 column has 200 angstrom pores. For this peptide, the larger pore size and reduced stationary phase surface area is the stronger variable that reduces the elution time. I recommend the C8 column for peptides larger than about 3,000 Daltons, although it did work very well here. Small, nonpolar peptides might benefit from the reduced retention of 200 angstrom C8 for these particular compounds. Does anyone have any questions now? Hello, I'm here, and we can take questions through the question and answer screen. Okay, we have a question: is will these techniques work for Hillic? And the answer is yes, it will. We can calculate gradients that way, and you do have to buffer your solvents the same way that you would for C18. Another question is my peptide prefers to run in basic solutions. Do you have any suggestions? And the first one that I have is most silica-based C18 columns don't run very well under basic conditions, although there are some that have a polymer chain holding the particle together, or another way of protecting the silica. But in general, silica dissolves under basic polar solvent systems. But if you're running a column that can't stand basic conditions or a polymeric reverse phase, it will run very well, and you can use, again, an ammonia buffer up at the pH range of around pH 9. The question I have is recommendations for a large peptide in terms of what column. Well, I would recommend for such a peptide the C8 with the large pore size that we have.
Jack, I just had a question posed. How much of a role do you think size, porosity has versus solvent choice and phase?
It depends on the size of the peptide. So I would say that in that case, the porosity would lead. However, the solvent choice probably plays a larger influence on exactly when a peptide elutes. The porosity plays a role with how much peptide that you can load more than anything. If the peptide doesn't interact with the column very well, it will tend to elute a little bit earlier, and it will tend to reduce your loading.